right, this is Mrs. McIntosh, Mrs. S. McIntosh, and I'm going to go through this lesson. You have guided notes in your lesson that you can fill out with Cami on your Chromebook, or if you're at home and you have a printer and you'd prefer to print them out and fill them out by hand while you watch the video, you can do that. But we're talking about the set of real numbers. That includes rational and irrational numbers. So we're going to go through some, first we're going to go through the sets and fill that in, and then we'll go through these definitions below. So this first set, the smallest set, would be the natural numbers. And as you remember from last week, we talked about the natural numbers are the counting numbers. 1, 2, 3, 4, and so on. I remember that the natural numbers are counting numbers because those are the numbers we naturally say, or we would naturally teach a little child if we're teaching them to count. We don't really say 0 when we're counting. That's not the natural way we count. So that's how I remember that. The next set up would be the whole numbers. The whole numbers are almost the same set as the natural numbers. The only difference is the whole numbers include that 0 that we don't say naturally. So the whole numbers are 0, 1, 2, 3, 4, 5, and so forth and so on up into positive infinity. Then we can get one set bigger than that even, and those are called integers. Integers are the whole numbers and their opposites. So the whole numbers, which are 0, 1, 2, 3, I'm going to write them up here. 0, 1, 2, 3, and so forth into infinity. And their opposites, which are the negatives. So going this other way, -1, -2, -3, and so on into negative infinity. Those are integers. Now, don't be fooled. Just because a number is negative does not make it an integer. If a number is negative, it still needs to be a negative version of a whole number. So -5 is an integer, but -5.5 is not an integer because that's not an opposite of a whole number. But -5.5 is part of the next group, which are rational numbers. Rational numbers. And the way I remember what rational means is I think about this first part of the word rational. The first 5 letters of the word rational spell ratio. And another word for ratio in math, I'm going to write it up here. You could write it somewhere on your screen. Another word for a ratio is fraction. A ratio is a fraction. And that's how I remember that the rational numbers are the fractions, the numbers in between. But notice that all the rational numbers are also, well, all the integers are also rational. And all the whole numbers are also integers and rational. And all the natural numbers are also whole and integers and rational. So some examples of rational numbers. 1/2, -0.7. Let's see, repeating decimals are rational. So if I had 0.3 repeated, that is rational. These are all rational numbers, and they could have another number in front of them. Let's do 2.8. That is a rational number. I could write every one of those as a fraction. So rational numbers have decimals that either terminate or repeat, and we'll talk more about that tomorrow. But right now, we're going to finish with our little chart here. Coming over here to this other separate set. This set, notice it doesn't cross over or intersect with the rational numbers at all. These are irrational numbers. If you remember from English, hopefully you learned this, if not, you will soon, the prefix ir means not, and then we have ratio. So these are not, I'm going to put this, ir means not, and ratio means fraction. So irrational means not a fraction. You cannot write it as a fraction. I'm going to give you several examples of irrational numbers. First one, and probably the most famous one that you all know and have heard of, is pi. Pi is irrational. In its decimal expansion, which looks like 3.1415920 something, 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 I think that's right, but I could be wrong. Anyway, we know that its decimal expansion goes on forever and never repeats. So that is what we're talking about when we talk about irrational numbers. Numbers whose decimal expansion goes on forever, we call that non-terminating, which means it doesn't stop, and it doesn't repeat. We call that non-repeating. So non-terminating, non-repeating decimals are irrational, but there are other ways to write them. So pi is irrational. The square root of a number that's not a perfect square, like 2, is irrational. Some of my classes know from last week, and I don't know if your teacher covered this or not, but a number that is a decimal, like this, 1 0, 1 1 0, 1 1 1 0, and so forth. That decimal number has a pattern. It's not what I would call a big ugly decimal, like what we see on the calculator if we put in the square root of 2. It's very organized and neat, and it has a pattern. It repeats the 1 0, but every time you do it, it adds another 1 in there. So it's not an exact repeat. Because it's not an exact repeat, even though it has a pattern, it is not rational. The ... tells you, the ... at the end tells you that that will continue that pattern forever. And even though it's a pattern, and even though we can predict what comes next, it's not repeating the exact same digit or group of digits forever. So it's non-repeating, non-terminating. It is irrational. So now that we've talked about those, let's write some definitions on these lines for rational and irrational numbers. I'm going to give you the technical math language definitions because it's good for us to learn math language. So a rational number, and you can underline that part that says ratio, is any number that can be written as a fraction of integers. Hopefully you wrote smaller than me, so you have space. As a fraction of integers. So it could be 1 over 2. It could be negative 7 over 5. It could be 17 over 3. Anything that's a fraction of integers. That means the top and the bottom both have to be integers. They can't be decimals. They can't be square roots. They can't be pi. Each of the numerator and the denominator have to be integers. The other condition is that the denominator cannot equal 0. And hopefully you all understand that fractions are all tiny little division problems. And we all know that we cannot divide by 0. If you didn't know that, ask Siri what happens when you divide by 0. She'll tell you. Okay, so an irrational number, ratio, is a a number that has a decimal expansion that is, and I'm going to run on to the next line here, but it kind of goes with this next stuff. So non-terminating and non-repeating. Okay? So a number that has a decimal expansion that is non-terminating and non-repeating. It has to be both. You might want to underline "and" there to remind you that it has to be both. Okay? Now, terminating. What did we say that terminate means? Terminating, just like the Terminator in the movies, terminate means to end. The Terminator was sent to end Sarah Connor's life. So terminating decimal is a decimal that ends. I am going to make this definition a little more technical to make it more specific, because do any of the decimals really end? Let's think about that for a second. If I'm doing a long division problem and I run out of digits at the end and I'm still not done dividing, what can I add on to the end of a decimal that I can keep adding forever and it won't change the value? That would be a 0. So a terminating decimal is a decimal expansion that terminates, which means ends, in zeros. That's how I'm going to write that, because I'm a mathematician, and mathematicians are basically lazy. So a terminating decimal is a decimal expansion that terminates in zeros. We don't usually write the zeros. So really, we can just think of it as a decimal that ends, like 2.75. There's an end to that. There's no dot, dot, dot. There's no bar over the top. It ends. Okay? And a repeating decimal is a decimal expansion. I'm just going to do quote, quote, decimal expansion that repeats the same, I should have done this in a different color, the same digit or group of digits forever. As you know, and I'm going to write the example over here, as you know, we write that by putting a bar over the top of the part that repeats. So, for instance, we have 0.3 repeated, or we could have 0.437 with just the 3 and the 7 repeating, something like that. So the digit or the group of digits. The 0.437 with the 3 and the 7 repeating would be 0.437373737373737. When can I stop saying 37? Never, because it goes on forever. Only I'm going to stop right now. Okay. Next part of your notes has these examples of numbers that we want to classify. So on A, we're going to classify the number. We're going to say if it's rational, irrational, if it's natural, whole, integer, rational, or irrational. So 9/5. If I put that in the calculator to get a decimal expansion, and maybe you have a calculator open, maybe you don't, but it would be 1.8. 1.8. So is that a natural number? No, we don't say 1.8 when we count. Is it a whole number? No, it's not a counting number or 0. Is it an integer? No, because it's not a whole number or a negative whole number. Is it rational? I know for a fact it's rational. You know how? Because it was a fraction to start with. If it's a fraction of integers, it is always rational. Okay? Then B, write as a decimal if possible, which we just did. It's 1.8. You can find the decimal value for any fraction by doing the division. Every fraction is a tiny little division problem. So that problem would be 9 divided by 5. When you put that in the calculator, 9 divided by 5, enter, you get 1.8. And for C, classify the decimal if possible. What kind of a decimal is 1.8? Well, I remember from, and you can look at the top part of your notes, 1.8 is a terminating decimal, and I'm going to abbreviate terminating because, again, mathematicians are basically lazy. If we can find a quicker, shorter way to write it, we will. Okay, let's do another example. I think you could do 7/15 on your own. So let's do -5, number 3. -5. Is -5 a counting number? 1, 2, 3. No, I don't say negatives when I count. Is -5 a whole number, a counting number, or 0? No, it's not. But it is an integer because it's a negative whole number. So I'm going to write integer, and you can, if you're on your Chromebook in Kami, you can put in a text box and type that, or you could write it with your mouse pad, whatever you want to do. Integer. Can we write that as a decimal? Can we write a whole number or a negative whole number as a decimal? We sure can. -5. We could add the decimal there and put a 0. In fact, I could put a bunch of zeros. I could put zeros forever. I'm not going to, but I could. So does that make that a terminating or repeating decimal? Well, it does repeat the zeros forever, but that was the definition of a terminating decimal, wasn't it? That it ends in repeated zeros. So it is a terminating decimal. Okay. Let's do 49 over 33. 49, I had to come get my calculator. 49 over 33. Is that a counting number? I don't know. I kind of need to know if it comes out even. So I'm going to get out a calculator. You could open Desmos.com and get out, if you click on Math Tools at the top of the page on Desmos.com, then you get a drop-down menu, and the second option is Scientific Calculator. You can put in 49 divided by 33. Oh, this looks an awful lot like a repeating decimal to me. So, is it a counting number? Hopefully you're looking at a value. I don't want to tell you what it is yet. So if you didn't get out a calculator, do it now. Is it a counting number? Pretty sure I don't say that number when I count. Is it a whole number? No, because it's not 0 or a counting number. Is it an integer? No, because it's not a whole number and it's not negative whole number. Is it rational? I know it's rational because it was a fraction to start with. But how else do I know it is rational? Well, let's write rational here, and then let's talk about the decimal expansion. Hopefully you've put it in your calculator by now, and you figured out that the decimal expansion is 1.48 with the 48 repeated. So 1.48 repeated. So what kind of decimal is that? Well, repeating means it doesn't terminate, it doesn't end. It means it's repeating. And I'm just going to write repeat right there. It is a repeating decimal. Okay, I want to do one more together, number 7, and then I want you to do the rest on your own as part of your practice today. So the next one I want to do is number 7, the square root of 10. The square root of 10. Is 10 a perfect square? I don't know. I can't remember. So what I'm going to do is I'm going to put it in the calculator. The square root, first I got to clear my calculator. The square root of 10. Ooh. Wow, I just got the answer on my calculator, and that is not a perfect square because that square root is not a pretty little integer. It is my class knows what I call these, big, ugly decimal. So this is a big, ugly decimal. And what does that tell me? When a square root gives me a big, ugly decimal, it means that it is irrational. Irrational. And I want to write the decimal expansion. Is it possible for me to write the whole thing? No, it's not. Because this fills up the whole answer part of my calculator, which tells me it goes on forever probably. And I see no repeat in here. So this, what I'm going to write is just several digits of it. I got 3.16227.766. I could go on, but I'm out of room, so I'm just going to put ... This calculator that I'm using gives me 1, 2, 3, 4, 5, 6, 7, 8 more digits. Remember, you have to ignore that last digit on your calculator because when your calculator runs out of room, it rounds the last thing. So that last digit may or may not be right. And what can I say about this decimal? I'm going to abbreviate it because it's a lot of words. But this is not a terminating decimal, is it? Nor is it a repeating decimal. It's non-terminating, non-repeating. So I'm going to just write the initials for that. Non-terminating, non-repeating. There we go. Non-terminating, non-repeating decimal. I want you to do the rest on your own after we finish the bottom part of our notes. So, here we have the main span of the Brooklyn Bridge is about 0.3 miles long. And I think you have a picture of a bridge on your notes. I don't because, oh, you don't either. Just kidding. So we don't have a picture of a bridge, but the Brooklyn Bridge is about 0.3 miles long. The main span of the Williamsburg Bridge is about 10/33 miles long. Which main span of which bridge is longer? So this is what I would do. I'm going to go Brooklyn Bridge right here, and they told me that is 0.3 miles long. Okay? Then I have the Williamsburg Bridge, and that was 10/33 miles long. It's hard for me to compare that fraction to that decimal, so what I'm going to do is turn the fraction into a decimal by doing the division. So in my calculator, I'm putting 10 divided by 33, enter. Oh, well, interesting. I got 0.30, repeating. The 303030303030 repeats forever. I can tell by looking at my calculator. So which one of those is bigger? 0.3 or 0.30 repeated? Sometimes it's hard to tell just by looking at that much. So what I like to do is write it a little longer. 0.3, and then I could add zeros forever without changing the value of that, and you all knew that. And then 0.303030. Okay, I'm getting the idea here. And see, I lined up one right on top of the other here. Let me wind these up, one right on top of the other there. And then I'm going to pretend like the decimal isn't there and just compare those numbers. Which one's bigger? 300,000 or 303,030? Pretty sure 303,030. So I'm going with the Williamsburg Bridge. The Williamsburg Bridge is longer. And if they asked me to explain how I knew, I would say because 0.30 repeated, or I could even use the term they gave me, 10/33, is greater than 0.3 or 3/10. There we go. Okay, this next question is a little bit tricky, and I want you to do it on your own, but I'm going to help you with the tricky part. It talks about parking lots and how far they are from a concert hall, but be careful because they ask which parking lot is closer. If it's closer, is the distance going to be greater or less than? If it's closer, pretty sure I want the number that is lower for the answer. All right, good luck with that practice. If you need help, you can either email your teacher, or if you're face-to-face, you can ask your teacher tomorrow. Have a good afternoon or whenever it is.